Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're gonna switch gears and some thing. The first one is on workflow. Plale. Go ahead.
There's a little issue. Watch one first. So. Guys don't. It's very acting. I'm a professor. I've done quite a bit of work in mostly earth, but in earth and earth science for the last whatever years. Is very much kind of the informatics computing, very much the informatics that's important in me. I'm also around data projects. It's actually data. It's targeting long-term preservation of sustainability, sustainability science data. And I put that in quotes. I say EE science because we talk about e-science and the fourth time talking about science. This is generally science. Something. This is here, but we talk about workflows. I mean, workflows basically work. This workflow are people do a task flow, whether it's a workflow that they need or not. Have they work on the process, try to make is 5 or 6 maybe years ago people science discovered basically we the difference between the workflow and the workflow in is business again problem. We're going to automate the e-discovery process. Well, we recognize, it's a process when the person you're working with doesn't even acknowledge there's a process. But we a little bit kind of what this is the cap. So workflow human activity might be something like this. There's some kind of abstract that retrieve multiple sources, versions of plotting, as this big step, and basically that workflow position, task administration, orchestration. That's for reason just workflow has a will tool and build workflow graphical. Change. So in their process, advantage using a workflow system, and again, anytime you're handing off a task, you've got to come with crop coming to to you that workflow systems know how to do well. Got one here. So if we take that we just with, we've got going to the left-hand corner here, all certainly the broader issue of cycle scientific. This diagram is from a report on sustainability of data preservation, Fran Berman report on. Look at what he's saying he wants to do preservation. Used to do of our this was before science. These two pieces were not. We would create products, distribute those products, and then at the end we would do some kind of long-term cure. This is where your digital libraries. There's our university data access, heavy human interaction. We're science has to product. Talk to that thematic and capturing on that aids scientists in some of the descriptive. So tying that to the work discussion, really pieces, and I'm just going to of three different things we're working on in this of workflows, and one of them is workflow value and is just scale computing, and I know in models, smaller models, so it's not. I don't want to overstate things. It's not by large models in some domains, in some domains, it's dominated by large scale processes. A bit of large, including and focused on in we talk. And then the piece, and this is where we're most recently doing a work. It's increasingly and your information scientific, and again, in response to national management, I'm sure. There's interest. There's a workflow system that are source are used. I've got a sub-workflow that runs on a Taverna, and I've got a sub-workflow that runs on Kepler. How do I make all that work? So what this was looking at is a top-level workflow system, and we were using Trident here. So this is a Trident workflow, runs on a Windows box that's got 4 nodes, A, B, E, and F. Node B calls out to a sub-workflow, and that sub-workflow might be Kepler, and it invokes the sub-workflow C and D. So that's the one case of the sub-workflow interoperability. And then the other case is where there's an activity in Trident F that calls out directly to a grid computing resource. It might execute a job on a big supercomputer or something like that. So really what we were doing is just analyzing this and analyzing it for several different cases basically, and just looking at the performance and then looking at some of the softer aspects of this hybrid interaction. And we did it for sequential. What we're seeing here is a sequential workflow that had both a compute intense and a data intense version. Compute intense was LinPack, and data intense was we were doing some computation. Sorry about that. We were doing computation here. That was more data compute in and out piece. We did it in a sequential way, and then we also did a heavily parallel way too, and then looked at the interactions. And this is what we tested. So again, we've got Trident as the workflow system sitting on system 1. Tried to get a baseline case. We called out to Workflow Foundation and ran the workflow all locally. That was kind of the baseline case. And then we called out to Kepler, and then to A. Return control to S, and C return control to S. So that's the difference between invoking a grid service directly and invoking through another orchestration engine, which is actually orchestrating that sub-workflow. Same thing on this side. We're executing through the ODE, which is an Apache workflow engine, through GFAC, which does similar stuff to through executing these services. And what are the pieces? There's that baseline execution environment, which is the top workflow activity, workflow, Kepler, and ODE, and resources. So this where we were workflow that's run. How much of that is visible at that layer, at that Trident? Those things are really critical to understanding the execution as a whole. So that. That Renzi is doing. This is involving Craig Maddox, who's University of Miami, who have an affiliation with Renzi. I think labs different model. With is no it's be done in a non-verbal way, so that is a plastic depends. We are work that's already been done, so we are taking that basically. .5 gigabytes out. So small data. we're like I said, this just got funded, so. And we explored using on Azure, and in order to do that, our Sigri worker service. I asked for it on top of Amazon is an infrastructure as a service, platform service. And I story at the table the result was big. Is more within, of course, is MapReduce oriented, so it's slightly different in its paradigm. So again, these are too early really to say much about because we were under stress of a deadline when we got it in. But these very early results suggest that your efficiency for Daytona is lower than for HP schedule. Province met early on. That's about the fact that we can't my mind important area. So anyway. extracts. Yeah. It's possibly some interesting. Through the process of kind of normalizing the file, comes information from that. Working on format migration. We can library things that we're real big on is, you get something in one. People that know OAIS, it's the model. It's the will go to and build these Google these. Develop these of workflows. Right. I was 75% environmental science use Excel, so I mean that's one of the reasons why we adopted. I was there's look at spectrum continuity. There's your structures together around their instruments, and they're all variable. They're all all kind of model. These are hydrologists. Just model. Sorry. So look at. I think you're one of the more difficult communities. Think about community that does have defined. I spent many years with knowledge confidence of what test. But pretty a little bit of a challenge. But I think the workflows maybe ability bringing pieces of data maybe people well by things with the additional work tool that target community virtual to any community where Carol Mike that's UK and global content not use workflow that's some of the focus. So they're focusing deploying on the large scale resource. You're saying something completely different. Is saying that I've it's a good one, right? Okay. And work and have. I mean, there's an assumption there. These two workflows. Interesting. That kind of issue would be known. Next. So that's where I've done a fair amount of work. Provenance lines up in a couple of areas. There's a provenance of data product, and then there's a provenance of the process. So more attention in terms of quality on the provenance of the data product, and because that argument, press. But I agree with you. Were we established process contribute to giving the quality?
studies that we have at all, part of the reason that these two agencies are interested in on the same the CERC, the two agencies actually had a memorandum of understanding. Wouldn't look like they were over. They on the climate center to have that. A number of years ago, the federal agencies that manage fish and wildlife started getting so they said, okay, we need to figure out a way to bring climate science into these decisions, and that was the motivation to create this of ACS country. The climate science centers, all 8 of them, have created. Them have issued request proposals, and those are being evaluated. They expect a decision, and that will help find research efforts with these other folks around. Climate research piece. Research to some, there's a little bit coastal, some on envisioning future integrated on the population growth and use change. This is the process of defining research. We now have a research agenda, among which is the integrated scenarios of climate hydrology involves different processes. So these are the research activities for the CERC. Integrated scenario development mentioned. We spent a lot of time region workshops doing CERC among natural resources and others, trying to find what climate information they needed, and this guided the creation of this list. We're also heavily involved in the U.S. National Climate Northwest contribution to that. And it's been very this time. NSF project in the Willamette River Basin in Western Oregon to try to articulate, this is the one I mentioned earlier, how different stressors are unfolding in the landscape, and do scenario planning with decision makers. And we're going to attempt this plane in Idaho, possibly a little northwest Puget Olympic Peninsula. We have who's working with a state agency to do climate hazard risk mapping. We've teamed up with some water utilities and water. They attempt to bring climate science into their decisions. We've been involved in the renegotiation of the treaty, which the treaty itself will substantially 20 to the advantage of to make a in 2015 to renegotiate the for changes, and so there's some effort to include climate science as well. I now have set for applications and large practical interest in science a little bit the actual task of modeling. Climate modeling computer program represents properties of the ocean surface and frozen parts built on what we observe about the world. And we those models try to what will happen if something changes. Of course, as with any scientific endeavor, there are uncertainties. Factors know exactly, so quantifying the effect of those unknowns is a very important thing. Two unknowns we try to the future. First, change the atmosphere, stuff to it, and that consequence. How fast over 80 example. Will we choose a race path emissions by emphasizing renewable energy and energy efficiency for consumption? Collect go the route of higher consumption, less energy efficiency, and continued reliance on fossil fuels. The second piece is climate sensitivity. I'll explain that a little more. Challenge climate model. About what climate is going to be, they'll we need to know what it is in my watershed or my wetland. I've got a species, so there's to have very specific. But this relevance is direct odds. We typically at having very, very large scale study areas and complicated program. What's here are estimates of that would carbon dioxide, and all of the different studies on the right side use different approaches, different data sets in very different time periods. So the bottom two, EM, that's for less than 1,000 years ago. And what we've done is to look at relationships between solar output, carbon dioxide, Earth temperature to try to solar carbon dioxide. And the way this calculation is done up with a probability function as shown with all the curves. And then the bottom part of this diagram just takes the 95th percentiles of each of those and then also the I think it's median, the dot there. Well, there are a couple of interesting things about this. And one is the estimates of climate sensitivity almost all lie in the range of 2 to 4 degrees Celsius. So in other words, at the time when we double, there's a little will double CO2 century. Not the time we double CO2, but actually, near system catches up, we see temperature of 4 degrees. And that's constant. The second is look at color, except the bottom. They indicate a tail. Is the probability of having a double temperature increase more than 4 degrees is significant. And if we want to articulate what climate sensitivity would look like, 6, 7, 8 degrees Celsius, that becomes very worrisome. That's where Arctic disappears very rapidly in the summer, and we have very large shifts in vegetation and very large reductions in snow and snow. And so it's quite important for the future to know where. Now, climate global models that are used have a climate sensitivity 2 to 4 degrees. So when they are plus around best estimate of the climate sensitivity, none of them tell us what the world will look like at that level with the very high climate sensitivity. I'd also note that just very recently, another last glacial maximum study was published for sea surface temperature. There's a very small and lower climate sensitivity. It could be that that's a better way to estimate climate sensitivity, and that we are that we optimize. Yes. Yeah, I'm it's different. So here are some things that people want to know about the, how stream precipitation change. Urban cities are worried about stormwater drainage. Yesterday over in Burlington North Santa Fe Railroad is worried about landslides that perpetually bury the tracks, and they want those to get worse. Will that damage from windstorms increase or decrease? Droughts have many causes. It's not having less precipitation. It's also very warm winter in like the Northwest, where most of our summer water supply originates with snow. And you get a drought from a warm heat air station to have that on land. Also often in where coastal swelling is driven by winds and sets the biophysical context for the surface there. And then using climate models as inputs, kinds that impact fire. It's just an example from West Washington, a handful. So for the rest of you, we had this very dramatic event in December 2007. This is Interstate 5, the south Vancouver. River several days closed, and estimates for several days of lost economic activity just because of the impacts on trucking. So dropped all these stations 500%, and 13 months later, the same river flooded in the, and I would have included other photos. It looks almost exactly like. Question, is it? So moving into the space, a little context here. We want climate sensitivity. We want detail. We want lots of different variables. This is sort of a conceptual diagram of the space of climate modeling. So on the left represents spatial resolution. On the right, very coarse resolution global models. Typically now being run at 100 to 300 kilometers for a grid box. And then over to the left, and these regional models, which are typically run at anywhere from, well, there's some runs that are done at 1 to 4. More it would be maybe 25 kilometers the whole world. The y-axis of run. And a modeling builds a climate model. They make all sorts of choices as they processes. Those choices are parameter value. For instance, the entrainment coefficient that talks about how moisture in a cloud interacts with the dry air outside of the cloud. And, have a strong observational basis for making a choice. There are also effects the exact state of the atmosphere when you start your model. So you can start it on a have the same, but the initial from and with a different outcome. And so really we want a large number of uncertainties sort of for the effect. And there you can see this sort of different large done by the huge modeling, and very small numbers of runs typically done with a regional model. Typically one a few 3. And NARCAS acceptance was for coordinate and global modeling for the U.S. at a kilometer resolution. So it's medium resolution, relatively high number for the model. And the problem is what we want is with high number of runs and high spatial resolution. And you anticipated this line that regional prediction, which we call both climate and .NET. This is a way of having the both work. So we've got dozens of simulations at a 20 kilometer resolution. So you can play around with those. We can check initial conditions. We can and better. Our computer, it consists of 40,000 active volunteers who just sign up at prediction.net, the structure for computing, and then it just automatically. So definitely, as I said, 40,000 active volunteers. 10 years of this is going on. There have been 300 people who up and completed, and total model year global is 20 million models. This screen, one of the jobs that ran on my computer, is a regional model embedded in a global model, and what's here is just the temperature, the surface temperature field from the global model. It's very cute. You can make it so that the globe spins slowly, and you can see, the sun heating up the land. These works typically are regional is one. It takes 4 days to run that. Turning, many years, a lot of computers like processors usually 2 jobs, and now got 100 spare on. Earlier, we're working with the folks in the UK, and our research has several models that are to their global app model has had AM3P. The version here, you specify temperature, and then it calculates everything else. And for the best, we've embedded had model at 5 kilometer resolution. We specify the sea surface temperatures, or SS, 2010 using the actual observed values that happened. And then as we play the initial conditions, we'll first of a year we use the starting, the initial conditions or the atmosphere day. And each as I said, and we are in beta testing. The next phase of the project is to use sea surface temperature from the CMIP, the model comparison project. So, a few model values. Mentioned the physics. There are a number of parameters used that can be perturbed. The critical relative humidity at which clouds form. So if you take a box of air and you slowly cool it, you actually get to the point where there's where the air is saturated, it'll form clouds. If you think of the whole body behaving as just one thing, it'll take a long time for that to happen. But in real life, if the box is 25 clouds on a side, you might get clouds, little clouds start from here and there. So that'll happen when the humidity is a little less than 100%. And you can use spatial it's So we play around with the estimates. That the entrainment coefficients I mentioned before, having to for happens once the solar enters the atmosphere, and rough coefficient to do with this. It's called a hyper carefully perturbed values in different combinations to try to get on star. First step, seeing July 1980. And on the left, the observations, right? Notice the right is because higher statistical resolution, although the spatial resolution is the same in both of these. I should note that on the left, what I'm calling observation is actually basically a model that's been atmospheric structure from below and measurement things calculates a physically consistent to go with this observation. And that's updated every day or twice a day, and so you get something that's a little bit like a climate model space reality. So you can see a lot of very similar features in both of these. You know, the cold mountains, Sierra Nevada mountain color Celsius. You can see the main the very Columbia Plateau and the Snake River Plain. So, you know, it looks like reality for the most part. But if you take a distance of the two, there are a few patches that are not oceans, terrain, and see a little bit of that in the northern Sierra and the climate. Temperature warm in the northwest and two parts of the southwest. There were a couple of days of the thing. That's kind of the about as we expect to get with this level of detail. One of the things to do large on was to ask how much hinge the size on some. So this shows the estimated mean, monthly mean low temperature on the same thing on and for January you can see the time you get about on some you kind of slide at whatever for July that happens a lot earlier, so it sort of suggests that we could get a very few normal memory for summer temperatures. We've also looked at how the regionally averaged temperature trend analysis data that I showed earlier, calculated from station data. So the bottom is the observed warming trend over the western U.S. Is 1 degree century, 0.9 Celsius a year. We did our station, and on the deviation of in the region climate prediction, slightly 5 degrees per but pretty similar. And actually correlation between series points that goes to show how responsive the western U.S., if you average over a very large area and over the whole year, responsive with temperatures, but that's for the year fluctuations, and from other reasons that the upward trend in both the land and the ocean temperatures. So we can hope. Anyway, another piece of evidence, modelization, what we would do think with models. Look at the seasonality of the full statistical distribution over the main western US, and each is for the 6. For each month, all of the 100,000 available are plotted. Some, if you look at the bottom, these are 25th and 75th percentiles. Half of the station we didn't want to save every. In today, talk the guy else, and he sort of swathed heavy precipitation, very moist air, then the bullseye that area. These of the new and especially at up in relationship that you can then apply to the few observations you do. So the grad did most but going to use a little more. We've already done work with the data to add data. Interactive right now. And there's a little bit of here. With features of the brain, and you can see is December, but it's very brain is and you can things change ground. Look at this. This shows things. So you can actually restrict the data to only display And of course, the on a